Venus is described in school as Earth's twin, same size, same density, neighboring planet. What school leaves out is that Venus is an active volcanic world where it rains sulfuric acid, the surface pressure would crush a submarine, and it may have had oceans as recently as 700 million years ago. The twin comparison is real in terms of size. Venus has a radius of about 6,051 kilometers, compared to Earth's 6,371 kilometers, and a mass about 81% of Earth's. That is where the similarity ends and the extreme begins. Venus's atmosphere is 96.5% carbon dioxide, with a surface pressure of approximately 92 bar, equivalent to being 900 meters underwater on Earth. The Soviet Venera landers, which successfully reached the Venusian surface between 1970 and 1985, were built like bathyspheric pressure vessels and still only survived between 23 minutes and 2 hours before the environment destroyed them. No spacecraft has survived longer on Venus's surface. The surface temperature is approximately 465 degrees Celsius, hotter than Mercury, despite being farther from the Sun. This is the greenhouse effect, taken to its extreme conclusion. Venus's thick CO2 atmosphere traps solar energy so efficiently that the planet cannot radiate heat away. Night and day are essentially the same temperature because the atmosphere distributes and retains heat globally. This is what a runaway greenhouse effect produces, a planet-wide oven with no off switch. The rain of sulfuric acid falls from clouds that sit between roughly 45 and 65 kilometers altitude. The clouds are dense enough to make Venus the most reflective planet in the solar system, giving it that brilliant white appearance. But the acid rain never reaches the surface. The temperatures at low altitude are high enough that the droplets evaporate before they land, producing a perpetual acid mist in the lower atmosphere. Now here is what school almost certainly never covered. In 2023, a team led by Robert Herrick at the University of Alaska published analysis in Science showing that a volcanic vent on Venus had measurably changed shape between two Magellan spacecraft images taken 8 months apart in 1991. This is the first direct observational evidence of active volcanism on Venus. The planet is not geologically dead, it is changing now. Venus Express, ESA's orbiter that operated from 2006 to 2014, found evidence of hot spots on the surface, consistent with recent or ongoing volcanic activity. The Da Vinci and Veritas missions, planned by NASA, and Envision, planned by ESA, are designed specifically to map and measure Venusian volcanism with modern instruments. Active Venus changes everything about how we understand its catastrophic transformation. The transformation itself is the most dramatic story. Climate models and geological evidence suggest Venus may have had liquid water oceans for the first 2 to 3 billion years of its history, roughly as long as life took to diversify on Earth. The transition to its current state is called a runaway greenhouse event. As the sun gradually brightened over billions of years, Venus's oceans heated, evaporated, added water vapor to the atmosphere, which trapped more heat, which accelerated evaporation in an unstoppable feedback loop. Ultraviolet radiation then broke down the water vapor, hydrogen escaped to space, and the oceans were gone permanently. What we see today is the aftermath. This matters for exoplanet science. Venus-sized planets in the habitable zones of other stars are being detected regularly. Understanding whether Venus's transition was inevitable given its solar input, or whether it could have been avoided, directly affects estimates of how many potentially habitable worlds exist elsewhere. If Venus-type transitions are common, the universe may have far fewer genuinely inhabited worlds than optimistic models suggest. The phosphine controversy adds one more unsolved layer. In 2020, a team led by Jane Greaves reported detecting phosphine in Venus's atmosphere using radio telescopes. Phosphine on Earth is primarily produced by biological processes or industrial chemistry. The claim generated enormous scientific attention and dispute. Subsequent analysis challenged both the detection significance and the calibration of the data. As of 2024, the detection remains contested. No confirmed biological explanation is required. Abiotic chemistry in Venus's extreme conditions could potentially produce phosphine, but the debate has not been fully closed. Follow for more planetary science that goes past the school chapter. And tell me, if Venus once had oceans for billions of years, does that change how you think about whether it could have had life before the transformation?